Alright, hey students, this is your physics teacher, Miss Hu, and what I'll be covering in this video are the answers to the Marshall Cavendish Education Student Theory Workbook for Chapter 6, Energy, Work and Power. So this is for my students who have to do this work in my absence as I have another duty to cover. Let's get straight to it. Alright, so I'm going to go through the answers to this entire chapter, 6A all the way to 6F. But I'll be skipping some questions which are irrelevant. So for example, for 6A, I'm going to skip it because solving a word search is not going to help you in IGCSE. So let's get to question 2. So for question 2, complete the following sentences. Another name for strain energy, as you should have learned, is elastic energy. Whoops, elastic energy. Another name for thermal energy is internal energy. Okay, I'm just going to zoom in so that you can see the answers. Okay, if you've already completed this exercise, then of course skip to the exercise which you need help in. So let's get to the answer for question 3. Objects in motion, the store of energy is of course kinetic energy. For nuclear reactors, it's of course nuclear energy. Stretched and compressed springs would be elastic, or you can call it strain. Two names for the same type of energy. Dry cells. Some of you have asked me what dry cells are. They're basically cells like the batteries, but they're dry because they don't have liquid like the wet cells that are used in cars. So dry cells, of course, have chemical energy from which the energy will then be converted into other forms. And objects above the ground, that means that they're placed at a greater height. That's, of course, gravitational potential energy. If you have already done this, of course, you can self-assess and mark this yourself. Otherwise, I will check when you hand this up to me. So question 4. Some of you have done this and have gotten it wrong. So please do the correction. Okay, so energy stored at the start here means that what it starts off with and what you can expect at the end after the transformation and how the energy was transferred. So here's an example. Gravitational potential energy store of a stone was converted to kinetic energy store of a falling stone. And how was this energy transformed? By forces through mechanical work done. So for the chemical energy stored in the fuel at a power station, if you look at this, fuel at a power station is best or rather most likely converted into the kinetic energy store of an electric motor. So that's the one that's going to go here. Let me fix that. And this is, of course, done by electrical currents through electrical work done. Now, the internal energy store of a kettle is used to what? Boil water. So, of course, that will be converted into the internal energy store of water. And how that's done, it is of course by heating over here. Okay, kinetic energy store of a child falling. Luckily, they're not falling down and hurting themselves. It's because they're on a trampoline, and this is of course by forces because there's mechanical work done. Nuclear energy of the store of the sun would be converted into the internal energy store of a solar cell by electromagnetic waves because the sun releases electromagnetic waves. Infrared, ultraviolet, visible light, all of those are electromagnetic waves. So that's the answer for question 6A. Well, I'm just going to shift things around a little bit. Okay, so next, let's go into questions in exercise 6B. So, hold on, I just need to make some changes to my screen. All right, let's get started now. Okay, so for exercise 6B, use the words given to fill in the blanks in the sentences. Use each word once, more than once, or not at all. The principle of conservation of energy states that energy... I need to shift some windows around. Okay, obviously, as you've already learned this in class, energy cannot... Wait, I'm typing and nothing happens here. Energy cannot be created or destroyed. It can be, if you look at what's available here, it can be transferred. from one energy store to another. Whoops. So these are the best words that we can use from the word bank. All right, now let's get to the understanding question, right? Application question, rather. So for questions 2 to 5, choose the correct answer and write your choice in the brackets. Figure 6.1 shows the side view of a roller coaster track. The car is released from P. So what's happening in this diagram? For this diagram, you can see it starts at P. P is at a greater height compared to Q and R. That means at point P, the car with its occupants have the greatest gravitational potential energy. This gravitational potential energy would then be converted into kinetic energy as it moves down. So at the bottom here at Q, it has the greatest kinetic energy, the least gravitational potential energy because it's at the lowest point. And somehow it's able to go back up to R. Why? Because the kinetic energy here is converted back into some gravitational potential energy. But you can see R is lower than P, so it is likely that when it goes up here, it's still moving at quite a high speed because at point R, there is a mix of gravitational potential energy as well as kinetic energy. Throughout the entire journey, remember the total energy remains the same. Of course, do take note there could potentially be energy loss, although that's not what the question asked. So anyway, let's look at question 2. So which statement is true? So here it says kinetic energy store of the car at R is larger than its kinetic energy store at Q. Not true, right? Just going to put in some words here so that you know what's going on here. Just now I mentioned here, right, it has gravitational potential. You're going to write GPE over here. Okay, this one has kinetic energy here. This has both GPE as well as kinetic energy. Okay. Okay, so A is obviously wrong. B, kinetic energy store at P is larger than its gravitational potential energy store at R. Not true because P is at the highest point. It's got more GPE. GPE is gravitational potential energy, so this is not true. Gravitational potential energy store at Q is larger than at P. Obviously not true. Gravitational potential energy store of the car at R is larger than at Q. Yes, because it is at greater height. So this is true. That means the answer here for question 2 is D. That's how we reason out the answer. Let's look at question 3. A boy drops a ball from a height. Ignore the effects of air resistance. The total energy is, remember, we already learned the principle of conservation of energy. Energy cannot be created or destroyed, it can only change form. That means that the magnitude of the total energy will be the same. It's just that the energy exists in different forms. That means that, of course, the answer is that the energy is the same at all 3 points. That's why the answer is D. All right, let's move on to question 4. So an arrow is shot vertically upward with an initial speed of 10 meters per second. What is the maximum height the arrow can reach? So I know some students get stuck here because you know the kinetic energy equation is half mv squared, but the question is asking for the maximum height. So how do you solve this question? So this question is based on the understanding of the conservation of energy. I'm going to do a small little sketch here to help you visualize. If we have an arrow that we're going to shoot upwards, when it moves upwards, it doesn't start with zero energy. It's being released with an initial speed, which means there is kinetic energy at the bottom here. And as the arrow rises, this going up, this kinetic energy is then converted into gravitational potential energy. Okay, maybe for consistency's sake, I am going to just write this instead as KE and GPE. So this is the opposite of what's happening with the roller coaster. The roller coaster started with gravitational potential energy and was converted into kinetic energy. This is now kinetic energy converted into gravitational potential energy. So knowing this, you can therefore conclude that, okay, at the bottom of the position, at the point of release, it will have the most kinetic energy. As it goes up, as the arrow goes up, it loses kinetic energy, gains gravitational potential energy. Throughout the motion, the value of the total of the kinetic energy plus potential energy will be equal to the initial maximum. At the top of the motion, where it when it reaches the maximum height, it comes to a stop. That means there's no more kinetic energy. That's where it will have the greatest gravitational potential energy. Maximum kinetic energy at the bottom here is equal to the maximum gravitational potential energy at the top. So now we're going to do a side-by-side substitution. Kinetic energy formula is half mv squared, so I'll put that on the left side. And gravitational potential energy equation is mgh, which I'll put that on the right side. So you can cut m, and then we substitute v as 10, g is 9.8, h is unknown. So when we solve this, we're going to work this out, you should get 5.1 meters. So that's why the answer here is A. So that's what I'm going to write in the bracket here. The answer is A. So that's how you get the answer for question 4. Let's look at question 5. A 4 kilogram box slides from the top to the bottom of the ramp. As shown, the bottom of the ramp, speed of the box is 10 meters per second. Sometimes it helps to just label so that we know what's going on here. I'm just going to add a number here, 10 meters per second, so that I will remember the speed of the box is 10 meters per second at the bottom over there. Question wants us to calculate the total amount of energy lost by the box to the surroundings. What do they mean by this? It's because at the top of the ramp, at this point, this box has gravitational potential energy. Now, when we let this go, the box will start to slide down, and when it reaches the bottom, it will convert the energy to kinetic energy. So it's kind of the opposite to the arrow. It starts off with gravitational potential energy, and then as it goes down, it loses gravitational potential energy, gains kinetic energy. But the thing is, the question is asking us for the total amount of energy lost by the box to the surroundings. So why is the energy lost? Possibly due to friction, right? So there's heat generated. How do we figure this out? So at the top here, the maximum gravity, So how do we figure this out? So the maximum gravitational potential energy at the top would be converted into kinetic energy at the bottom and also heat loss. So again, we'll do a side-by-side substitution. This is, by the way, this is maximum GPE at the top. Maybe I should type it out because the writing is very, very, very bad. Okay, so maximum GPE at top is equal to the maximum KE at the bottom plus heat loss. I'll shrink this so that it can squeeze into the box. Okay, so the maximum GPE at the top is mgh. Kinetic energy is half mv squared. Heat loss is, of course, unknown. Okay, so now we'll do a substitution. So they've given us the mass. Mass of the box is 4. G, of course, is 9.8. The height is 6 meters, not 10, yeah? Because we're going by vertical height. Half mv squared. Let me write this out because this tool doesn't allow for squares. So half, m is 4, v is 10. So put here 10 squared plus heat loss. Okay, so you can't cut the mass because there's heat loss, which we don't have the equation of, but we're going to calculate what the total value of the heat loss is. So I'm going to work this out because I don't have the answers in hand. So when you calculate the left-hand side, you should get 235.2. And then for the kinetic energy, that would give us 200. Let me fill that in. 200 plus the heat loss. So of course, if you minus this correctly, you should get 35.2 joules. And that's why the answer is B for question 5. I'm going to make this larger. Okay, so that's how we solve for question 5. Now let's go on to exercise 6C. So we need to circle the correct equation. Work is force times distance moved in the direction of the force. That's why the answer, of course, is W equals to FD. Okay, explain Why a man who's walking at a uniform speed while carrying a heavy bag, there's no work? Remember I told you all in class, right? You can get a heavy box and there's no work done. Excuse me. So this is because when you want to calculate the work done has to be based on the force multiplied with the distance moved by the force in the same direction. So you can explain that the man is applying a vertical force on the back. Whoops, let me fix that. Force on the back. There is no horizontal force on the back. Okay. The distance traveled is a horizontal distance. There is no work done because there is no vertical distance traveled. So force times 0 equals 0, and there is no horizontal force done. You can write here 0 times d equals 0. Okay, you don't have to use these exact words, but something to this effect. Okay, I'm just simplifying it. I'm putting in equations here so that you understand why it's 0. Now let's move on to question 3. Okay, so for this is really easy because you just need to use the formula of work equals force times distance, and then you just rearrange the numbers accordingly. So of course, to get work done, 25 times 3 should give you 75 joules. Please do not forget the units, because without units, you're not going to get full marks. So in this case, in order to get the force, you just take the work divided by the distance, which should give you, let's see, 40,000 divided by 1,500, 160 Newton. And likewise, to calculate the distance traveled, it is 5 joules divided by 0.1, which should give you 50 meters. To solve question 4, of course, you just use the formula of work equals force times distance. So they want you to calculate the work done on the box by friction. They've given you the friction as well as the horizontal distance. So it's very straightforward. You just take the force, the frictional force, which is 50 Newton. Times the distance traveled, which is 3 meters. This should give you 150 joules. So please put the answer in the space provided here. The unit is already given to you. You're very lucky. Just put the number in there, 150 joules. Okay, for question B, a box is placed in the lift goes up, and they want you to calculate the work done. Now, because it's a vertical distance traveled, the force applied would be equal to the weight of the object, because there is force pulling it up to overcome the weight of the object. That's why when you want to solve this using this formula, for the value of the force, you take the weight of the box. So you need to convert the value of the mass of 12 kilogram into Newton by multiplying it with 9.8. That's why we put 12 times 9.8, and then you multiply it with the height, the vertical height. So let's do a quick calculation. And you should get 3528 joules. Now, remember that for IGCSE, they prefer you to write to 2 or 3 significant figures. So that's why I'm going to round this to 3,500, which is 2 significant figures. That's how you solve question 4. Let's go on to let's go on to exercise 6D. So for this question, against a word bank, you need to use the words to fill in the blanks. Okay, you might use each word once, more than once, or not at all. Fossil fuels and biofuels, of course, have chemical energy. Geothermal resources, as you should have read in your textbook, geothermal is basically heat, right? So it's a thermal store of energy. It's a naturally occurring thermal store of energy. Okay, so here we need to figure out what goes in these blanks here. So in hydroelectric and blank power stations, energy in the blank store of water is transferred mechanically to drive generators to produce electricity. So this is about water, and water is being used to make the generators rotate to produce electricity. So looking at the word bank here, the best answer, of course, is tidal, because none of the others are energy resources like hydroelectric. So hydroelectric and tidal power stations, right? So in a the energy in the, okay, so the water has to transfer mechanically to drive generators. So obviously that will be kinetic because the water will move and then make the generators rotate in order to generate electricity. Uranium, some of you see this and get very excited, right? Ooh, obviously uranium is nuclear. So uranium is used in nuclear reactors. Nuclear reactors. To heat water to steam that turns turbines. Yes, you should have read this in your textbook, right? The turbines are connected to generators which then produce electricity. If there's anything that you don't understand here, ask me and I'll explain this in class. Let's move on to question 2. So for question 2, choose the correct answer and write your answers in the brackets. What is a process that releases the stored energy in the sun? If you've read this in your textbook, then you know it obviously has to be nuclear fusion. Nuclear fusion is a process of hydrogen isotopes combining to form helium atoms. That's why the answer in this case is D. Let's go on to question 3. Am I on the correct page? Yes, I am. Okay, question 3. Draw a ring around 3 energy resources for which the sun is not the source of energy. You do need to know this. This is something that they always test in IGCSE. When you see this, the sun, right, is not the source of energy. Basically, almost all energy resources come from the sun except 3. Just remember T and G, tidal, nuclear, geothermal. These are the 3 for which the sun is not a source. The rest are all because of the sun. That means all the other energy resources exist because of the sun. So T and G, tidal, nuclear, and geothermal. So that's the answer. The rest are all the rest of the energy resources exist due to the presence of the sun, or are because of the sun. Okay, let's move on. The efficiency of a coal-fired power station is 40%. Explains what this means. So remember, efficiency is about the useful output power. So how you can explain this is basically you can say that only 40% of the total energy stored, you can say stored in the coal, is converted into this is power station. So we want to say it's converted to a useful form, but because they've already mentioned specifically this is a power station, the useful form, of course, is electrical energy, right? Because the coal-fired power station is to generate power, so it's converted into electrical energy. So that's how you can explain what this means. Basically, we are explaining how 40% efficiency applies to the concept of a coal-fired power station. We talk about the input and the output. All right, let's go on to question 5. Figure 6.4 shows a Sankey diagram for an electric motor. The electric current in a motor transfers 500 joules of energy as some useful energy in a kinetic store and 80 joules wasted energy in the thermal store. So on figure 6.4, fill in the blank. So this is a Sankey diagram. Remember that whatever goes straight is the useful output, and it's always drawn to scale. That means the ratio of the size of the arrow does show its actual percentages. But anyway, so the question did give you the numbers, right? So we start off with 500 joules. 80 joules has been lost, or rather wasted, in the form of thermal energy. So obviously the balance has to be the useful. So 500 minus 80, of course, would give you 420 joules. So you fill that number in that blank over there. The efficiency is calculated using the useful output over the total input times 100%. So I'll write it out here. Efficiency equals to, we'll just put the number straight in. So it's 420 divided by 500. I'm just going to push the number at the bottom here. I'm going to use the pen to draw a line. Okay, and then this is, of course, times 100%. So when you calculate this, I'll calculate that real quick. You should get 84%. And that's the number we write in here, because there's a percentage sign here, so you just need to write the magnitude, which is 84. That's how you solve question 5. Now let's go on to exercise 6E. Write down two equations for calculating power, where P equals power, work, W equals work done, and T is time, and triangle E, change in. And remember, the triangle means the change in, or in the difference in value. So this is, I've already given you the equations in class. So you should know already that power can be calculated as the work done over time, or energy over time. In this case, because I use triangle E, you write here triangle E. Okay? All right, let's continue. So the question 2 says, all right, a 54 kilogram girl uses the stairs to cover a vertical distance of 8 meters in 48 seconds. Calculate the minimum power she uses. So how to solve this? They told you that she uses the stairs. So now how you can visualize this is, let me draw it this way. So these are the stairs. Okay, so the vertical height here is 8 meters, and this girl is moving up. Okay, the girl's very big, I know. So imagine she's moving up the stairs. Okay, how do we calculate this? What is the force used in this case, or the work done, rather? So they gave you her mass, and they gave you the value of G, because this will enable you to calculate her weight. So what is the force then? The force is her weight, because if she weighs this amount, she needs to use force in the opposite direction to make herself go up. So she's going up, 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 and you only need to take into account her weight, because the weight is basically vertical downwards, right? That's the weight, by the way, in case you're wondering. We make this look not so bad. So if her weight is pulling her down, she applies a force upwards in the directly opposite direction. Direct opposite direction. So if you look at the distance traveled, the distance has to be in the direction of the force. So that's why we can take the vertical height for her work done. That's why you'll be wondering, isn't she moving at a diagonal? Yes, she is. But in this case, because we are taking the distance in the direction of the force, we take the vertical height 8 meters because it's in the direction of the force she applies, which is opposite to her weight. So remember, like the box thing, you could be moving the box, but if you're carrying the box with a vertical force and you move whichever direction, there's no work done. You only take the distance covered in the direction of the force. Okay, long story short, to keep it simple, you just take, let me type this out because my writing is really bad. The work done is force times distance. For the force, take her weight. Her weight is, wait, it's blocking, 54 kilograms. So 54 kilograms, whoops, times 9.8 to get her weight. And you multiply this weight with distance, which is 8 meters. Calculating this, you should get 4233.6 joules. Now, what we want to do is we want to, is this correct? 54 times 9.8, yes, it's correct. Okay, so taking this then, we want to calculate her power. You just take this work divided by the time. So let's write it here. I'm going to, because the tool doesn't allow me to do fractions, I'm going to write it out. Bear with my writing for a moment. So you have 4233.6 divided by 48 seconds, which should give you 88.2 watts. So I'm going to type it out here for you, 88.2 watts. So of course, final answer, you can just write to two significant figures, which is 88. Not 90, 90 is one significant figure, okay, 88. Okay, so that's how you solve question 2. Okay, question 3. A 1100 watt kettle takes 1 minute to boil some water. Calculate the total electrical work done. So if we know that power is work done over time, therefore work done is basically power times time. So if power is 1100, time is 1 minute, but remember that you cannot write the time in minute, it has to be seconds. So that's why we multiply it with 60 seconds. That gives us 66,000 joules. So that's why we write here 66,000 joules. All right, question B. is the energy transferred to the water more than, less than, or the same as electrical work done by the kettle? Think about it. There will always be energy lost to the surrounding, right? So it obviously cannot be more than. Where does the magic energy come from? Okay, not the same because there's always energy loss. Therefore, the answer is less than. So energy transferred is less than, oh my gosh, the energy transferred is less than the electrical work done by the kettle because there is some energy transferred, or you can say lost, to the surrounding. Okay, so that's your answer. So where does it, if you're wondering what do you mean by the energy loss to the surrounding could be the air, for example. That means some of the heat energy is lost to the air, or even the body of the kettle itself, like whether it's plastic or metals, the kettle will absorb some of the heat energy. So not all the energy was absorbed by the water. Okay, now let's go on to 6F. Okay, so for 6F, a child of mass 28 kilogram stands on a trampoline. Okay, state the energy stored that is increased when the energy stands on a trampoline. So there are springs as shown here in the diagram. So if you've ever been on a trampoline, you know, okay, when you stand there, of course, you're stretching the surface a bit. So the spring as well as the surface, the material of the trampoline fabric, of course, will be stretched a bit, which both are basically elastic energy. So we're just going to write elastic. You can call it strain energy as well. You don't have to write both. You can just write elastic energy only or strain energy. So this bracket is just to indicate that that's the alternative answer. Okay. Okay, so the child bounces up and down. She's pushed upwards when the stretched surface of the trampoline contracts. When she leaves the trampoline and starts to travel upwards at a speed of 5 meters per second, like the arrow. Psh. So calculate her kinetic energy when she leaves the trampoline. So this is pretty straightforward. They've given you her speed and a mass. So if you want to calculate her kinetic energy, it is by using the equation half mv squared. So let's substitute m as 28 and v as 5. Okay, one thing that a lot of students tend to forget is to square. So don't forget to square the value of the speed. So the total kinetic energy that you should obtain over here is 350 joules. So that's the value you write in here. Now notice that for this particular space, units are not provided, so you must write the unit with your final answer. Whenever in doubt, just write the unit anyway. You will not be penalized for writing an extra unit, but you will be penalized if you never wrote a unit and there was no unit there. So then you completely get no marks for the final answer. So better to be safe than sorry. Okay, C, calculate the maximum possible height you can reach from the trampoline. Give your answer to two significant figures. So remember, this is like the arrow question, right? So her kinetic energy will then be converted to gravitational potential energy because as she moves upwards, she comes to a stop. That's the maximum potential height that she can reach. That means that the maximum gravitational potential energy she will have would be equal to the maximum kinetic energy, which she has as she just left the trampoline. That's equal to the value you calculated in B. So that's equals to 350. The formula for gravitational potential energy, of course, is mgh. So this will be equal to 350. So when you do the substitution here, m is tadi berapa? 28, right? Yeah, so 28. G is, of course, 9.8, and h is unknown, but you know the total is equal to 350. So when you solve this, you will get a value of 1.28 meters. Where is it? Okay, so h equals 1.28 meters, but remember that you can always, sorry, let me rephrase. Question already says, give your answer to two significant figures, which means that you can write this as, you have to write this as 1.3 meters. So that's the answer you write in the final space provided. By the way, one thing I find some students do is they write two numbers in the space, only write one number at a time. Don't do this. Some students, they do this, 1.28 meters, whoops. They write 1.28 meters equals, don't do this, there's two numbers in there, you'll be marked wrong. They only want one final answer, that's what you write. Okay, now D, explain why the actual height she reaches is slightly less than your answer in C. In an ideal world, there will be no energy loss, so whatever gravitational potential energy she has, is like you would see, oh, all the kinetic energy she has is converted completely into gravitational potential energy. But the reality is that some energy will be lost to the surrounding because there's air resistance. So there's some thermal energy that has been generated due to the friction or air resistance, or even friction with the surface of the trampoline and the springs and all that. So that's why there's always a bit of energy loss. So if there's energy loss, that means that the gravitational potential energy that she has will be less than what we calculated or what we assumed in C. That's why the height will not be equal to this value. So what you can say is that sum of the energy is transferred to the surrounding. Oh my goodness, my spelling. Such as air. You can even say she is doing, oh my gosh, doing work against, my typing is usually better than this, means air resistance. Okay? If you wrote also, like what I said just now, some energy is lost to surrounding, it's also accepted. Okay, something to this effect. Let's go on to question 2. Okay, a stationary train starts to move when a driving force of 35,000 Newton acts on it. State the energy stored that increases when it starts to move. When it starts to move, obviously it's gaining kinetic energy. Okay, the train travels 2 kilometers along a straight horizontal track. Calculate the work done by the driving force on the train. This is, of course, based on the formula W equals to FD. They've given you the force, which is 35,000. You just need to multiply this with the distance traveled, which is 2 kilometers. Now, you cannot write 2. The value has to be in meters. So that's why you got to convert kilometers to meters, which is basically 2,000. So this would give you 70. There are 6 zeros. 1, 2, 3, 1, 2, 3. So it's 70 million joules. You can write this in standard form. Remember, standard form is preferred for very large numbers so that you don't mess up the number of zeros, as I've mentioned this in class. So don't just write 7, write 7.0 because you need 2 significant figures. Okay, 7.0 times 10 to the power of 7 joules. Mass of the train is 750,000 kilograms. Calculate the maximum speed. So this is the work done. That means that you can assume some of the work done is, no, let's assume that the work done will be converted into kinetic energy. So if all the work was converted into kinetic energy, that means that you can equate the maximum kinetic energy to 70 million joules. So I'm going to write here, maximum kinetic energy. No, let's not write, because writing is bad, right? So let's type it out. So the maximum kinetic energy will be equal to the work done by the driving force, which is 70 million joules. Okay, now the formula for kinetic energy is half mv squared. This will be equal to 70 million. Then let's substitute. M is given as 750,000. V is unknown. Okay, so from here, let's solve this. Okay, I'm going to use my calculator. You should get 13.66. If you didn't, you check your calculation again, okay? 13.66 meters per second. But remember, we prefer 2 to 3 significant figures. 2 is actually the preferred one. So you can just write the answer straight away. Rounding this to 2 significant figures, you will get 14 meters per second. So that's how we get the answer for question 2. Let's go on to question 3. So for question 3, a nuclear power station generates electrical energy. The main stages are listed, they're not in the correct order. So this one, if you read your textbook or if you watch my video on how a nuclear power station generates electrical energy, then you can answer this question, right? So it starts off with the nuclear power station uses a uranium as a fuel. Okay, from there, okay, let's see, electrical energy is produced, fission, so starting from the fuel, if they talk about uranium, obviously the next step has to be about the uranium itself. So the next bit is about the fission of the uranium nuclei, releasing thermal energy. If you don't know nuclear fission, we will cover that in Unit 5, or you can watch my video on nuclear fission and nuclear fusion. Okay, next, once the nuclear fission has occurred, okay, you can't produce electrical energy straight away, right? It says it releases thermal energy. The thermal energy needs to go somewhere first. So not to the turbine. Obviously, they've already given you the hint here. Thermal energy heats water to produce steam. So once there's steam, the steam is then used to drive the turbine. So turbine basically is connected to a generator. The water boils, produces steam. The steam will then turn the turbine, which is connected to the generator. So the turbine next drives the generator. That's why the next answer here is G. And then once the generator is driven, then yes, you have electrical energy is produced, which then will be transmitted. So that's the answer for question 3A. 3B, electrical energy from the power station is used to power two different lamps. The figure 6.6 shows how the light outputs from two types of lamp vary with the power input. So we have the filament lamp here and LED lamp with another graph over here. You got the light output on the x-axis, power input on the y-axis. The experiment requires a lamp with a light output of 70 joules per second. For the LED and filament lamp, determine the input power required to give a light output of 70 joules per second. So the output is 70, which means that the number you're looking for is here, 70, which is along here. So you need to, look at your graph. Use a pencil and a ruler, please. I'm using my digital one, so it's not so easy to use, okay? So from here, let's zoom in. You can see that for the LED lamp, 70 joules per second is 100 watts. So the answer for LED is 100. Ideally, you should draw with a pen and pencil to show how you got the answer. That means you need to do this, okay? You need to show on the graph. That's normally how you get full marks for this kind of question. For the filament lamp, it's up to here. This is 500. Okay, make sure you draw properly, okay? Do as I say, don't do as I do. Okay, so this is 500 watts. Okay, explain why using LED lamps is better for the environment. Use information from figure 6.6 in your answer. So you can see that for both the filament lamp and LED lamp, if we compare the same light output of 70 joules per second, that means that these two lamps will have the same brightness. But the filament lamp requires a much greater input, 500 watts compared to the LED's only 100 watts. That means a lot more energy is lost when you use a filament lamp compared to the LED. Okay. So what you can write here is, okay, LED lamps require a much lower input power compared to the filament lamp. There is less, you can say there's less wasted power compared to the filament lamp. Because you got to talk about the environment, you can also maybe throw in an explanation as to how the generation of electricity is not good for the environment. Okay, so we can say that many energy resources used to generate, not energy resource, let me rephrase that. Many methods to generate electricity produces a lot of harmful byproducts which are bad for the environment. Hence, the less energy wasted, the less energy needed, so less harmful products will be released. Something to that effect. Okay, I know you can't read it, and it's too many words here. I'm over-explaining it, but generally, you just need to talk about the LEDs requiring a much lower input with less wasted power, and that because it generates less electricity, so there's less harmful products generated. Okay, so let's move on to question 4. 4a, a force is used to move an object from the Earth's surface to a greater height. Explain why the gravitational potential energy increases. You can explain here. Because the height of the object increases. GPE, let's write in full. Gravitational potential energy is calculated using mgh. Therefore, when h increases, GPE increases. So we can use a short form GPE here because the question wrote GPE. Otherwise, try to write it in full all the time. Figure 6.7 shows a train moving up towards the top of a mountain. It transports 80 passengers, each of an average mass of 65 kilograms through a vertical height of 1,600 meters. So to calculate the GPE, we use the formula of mgh. Mass is 65 kilograms for each passenger, and there's a total of 80 passengers. So we're going to multiply this with 80 passengers. G is 9.8 and H is 1,600. So using your calculator, calculate this, you should get 81536,000 joules. But remember, we don't have to write it with so many digits. We always want to write it to two significant figures. And I'm going to write this in standard form because it makes it a lot easier for the examiner to mark. So we'll just write, okay, let's round this to 8.2 times 10 to the power of 7 joules. So that will be the answer for question 4b. Question 4c. The engine of the train has a power of 1,500 kilowatts. Time taken is 30 minutes. Efficiency, you're going to calculate the efficiency for it to reach. Right, so what we're going to do first, you can solve this two ways. Either calculate the input energy, or you can calculate the output power, because we have the increase in GPE. So this is the useful output because this was the final product where we can finally get the passengers to the top of the mountain. The input is 1,500 kilowatts. So what I'm going to do now is I'm going to calculate the output power, which is basically, we'll just put 8, 2. So we're going to put 8, 2, 0, 0, whoops, 0, 0, 0, 0, 0, 0. And we're going to divide this by 30 minutes. 30 minutes times 60 seconds. And this would give us 45555. Okay, I'll just put this as 45556 watts. So now we're going to take this output power and divide it by the input power. Efficiency equals to, okay, whoops, 45556 divided by 1,500 kilowatts. So remember, you got to change it to watts because kilowatts is basically times 1,000 watts. Okay, so this is going to be multiplied with 100%. Which would give us 3.03%. That is pathetic. 3.037 actually, so it's 3.04 which essentially is actually 3.0%. We write the three significant figures, so 3.0%. Yes, that's pathetic. That means there's 97% energy lost in other forms, possibly sound and heat. Now, if let's say you didn't use this method and you calculated using energy instead, that also works. So you could calculate instead, given you input power. So this is method 1. So I'm just going to label here as method number 1. So just put here number 1. Okay, method number 2 is by taking the power and converting into energy instead. So we're going to count an input energy by taking power times time. So that's 1,500 kilowatts, so another 3 zeros there, times 30 minutes, times 60 seconds, and that gives us a very big number. So 2.7 times 10 to the power of 369. So that's 9 joules. So then what you want to do, what you can do next is when you calculate efficiency, you take the input energy, the output energy, which was 8.2 times 10 to the power of 7 joules. 8.2 times 10 to the power of 7 joules divided by that input energy of 2.7. So that's 2.7 times 10 to the power of 9. Let me use my pen to write this. So this is 8.2 divided by, times 10 to the power 7. Then this is by 9. We're going to times 100% over here. So when you calculate this, you should get the same number actually. Yes, we get the same pathetic number, not pathetic, very low number of 3.04%, which is basically 3.0%. So both methods are correct. Either you calculate them in the form of power or the form of energy, and you still get the correct answer. And that's pretty much it. So yes, so once you've done this, make sure you hand up your books, and if there's anything you don't understand, let me know so that I can explain to you again in class.